sampling distributions and the central limit theorem. The central limit theorem is a very important theorem in statistics. It is what allows us to use sampling distributions in many, many situations. We're still using the same terminology. So remember, our parameters are mu, the population mean, p, the population proportion, x bar is a sample mean or a statistic, and p hat is a sample proportion. Those are both statistics. The central limit theorem really concerns itself with sample means, okay? And specifically, what happens when your population you're sampling from is not a normal population to begin with, okay? Or if we don't know if the population is normal to begin with, okay? Which is often the case when you're sampling out in the real world. You may be sampling from a situation where you don't know a lot about the population to begin with. So the central limit theorem allows us to still use the rules of our sampling distributions if certain conditions are met. Now, the graph you're seeing on the screen, these are the NFL player salaries in 2020, so this year. Notice that there are 1,910 players in the league, okay, that were in this population, and the average salary was $1,828,332.58 or 59 cents. The median salary was $825,000, and the standard deviation was about $2,715,755. Now notice the mean is much bigger than the median, which implies that this distribution is skewed right. And that is exactly what you're seeing on the graph, that this distribution is heavily skewed right, okay? So this population is obviously not normal, okay? But what happens when we start taking samples from this distribution? So this is the sampling distribution of samples of size 5. So imagine that we did a meta experiment, okay, where we took 1,000 samples of size 5, okay, and then I graphed them on the screen. So this is a sampling distribution. Each dot represents a sample of 5 NFL players taken randomly. So the average of this graph, the average salary was $1,853,327. Notice that's very close to the actual population mean. Okay, we're only off by about $25,000, which when you're talking about numbers this big is less than 1%. Okay, so those two are basically the same when you're talking about this magnitude of numbers. Then the standard deviation is about 1.1 million, about 1.2 million actually if you round. So this distribution still looks skewed right, but it's not quite as skewed right as the population was to begin with. Here's another sampling distribution. This time we took samples of size 10. Okay, so each dot here represents the average of 10 randomly selected NFL players. And again, we chose 1,000 samples. So we're getting towards that meta experiment. Okay, and you can see the mean of this distribution is about 1.8 million, and which again is very close to the actual answer. And again, we're off less than 1% from our sample means to our actual population mean. Okay, and notice it's not, it's getting a little bit less skewed when I took a sample size of 10 than it was of 5. Here is a sample size of 20. Okay, notice now we've lost that big tail over here. Okay, you can see that this is starting to level out and it's starting to become bell-shaped possibly a little bit. We still have a little bit of tail over here, but it's starting to lose that. These dots represent samples of size 20. Okay, so we went from 5 to 10 to 20, so we're doubling our sample size each time. Notice the mean of all of these samples was 1.8 million, and our population was 1.8 million, so we're still estimating this within 1% of the total, so that's great. But notice our standard deviation has dropped now considerably. We're now about $500,000, we're a little under $600,000 standard deviation. So our standard deviation is decreasing. Our mean is still staying the same, and our graph has lost a little bit of its skew, okay? Here's a sample size of 30. Okay, and we know from our sample mean lesson that once we hit a sample size of 30 or more, that our distribution, we can start assuming that it is approximately normal. Okay, now there's still a little tail over here, but in general at this point, we could start using z-scores and feel like they're pretty accurate. And notice our mean of this sampling distribution is very close to our population mean. Okay, so 30 is kind of the magic number. Once we hit that, we have some really good information. Look, our standard deviation has now dropped below $500,000, which means our numbers are getting more accurate. You can think of the standard deviation as, you know, the measure of the error, okay, the sampling variability, and as our sample size is increasing, our error or our sampling variability is decreasing. Okay. And now, just for fun, we jump to a sample size of 100 taken from this population, and notice again our sample mean is very close, under 1% of our population mean. And now look at our standard deviation, or our error has dropped to $265,000. So as our sample size has increased, our standard deviation has decreased. Okay, and if you look now, you know, this is becoming more and more bell-shaped as we go. Okay, so we started off with a distribution that was wildly skewed right, but by taking increased sample sizes as we go, you might notice that our sampling distributions have stopped being so strongly skewed and are becoming more and more bell-shaped as we go, as we move. So here are the 6 graphs, so you can see them all at once. Remember, our population was heavily skewed to the right. That's this one up here. But as we go, you know, sample size of 5, we were a little less skewed. Sample size of 10, a little less skewed. Once we get to 20, we're starting to see the bell shape occur. Once we get to 30, at that point, we consider it pretty bell-shaped and enough to use a z-score. And then at 100, you can see that it's more and more approximately normal as we go. And notice that as the sample size increased, our accuracy of our samples increased. You can see the standard deviation gets lower and lower the bigger the sample we take. Okay, so that's the two things that happen. As we take bigger and bigger samples from this skewed population, the sampling distributions become more and more normal as the sample size increases, and our standard deviation decreases, meaning our sample distributions become more accurate and more centered around the mean. Okay. So the central limit theorem. The CLT, is how we abbreviate that, states that the sampling distribution of any statistic, okay, now any statistic means for any population, okay, and it could be for a sample means, it could be for a standard deviation, it could be for a variance, but any statistic will be approximately normal if the sample size is large enough. Generally, a sample size is considered large enough if it's greater than or equal to 30 for sample means, and n times p greater than or equal to 10, and n times 1 minus p greater than or equal to 10 for proportions. And remember, we said some textbooks use 5, so we can use 5 as well as our minimums. Okay, so this is big because it means it does not matter what the population distribution is. Okay, as long as I take a big enough sample, my sampling distribution will be approximately normal. So this allows us to sample from any population, and as long as we know we've taken a big enough sample, we can assume the sampling distribution will be approximately normal. And that's a big deal because then I can use the standard normal distribution and z-scores to answer questions about how accurate samples might be. Okay, so this is a very important theorem in statistics. Some people say it's the most important theorem in statistics because it allows us to use this sampling distribution idea. So here's just some examples, some more examples. If you start off with a population that's uniform, okay, now this whole top row, these are population distributions. And this one is skewed right, kind of like our NFL players. This one is a uniform distribution. Remember, those are flat. And then this one's a bimodal distribution. Notice there's two peaks, one over here and one over here. It's still symmetric. The mean is still in the middle. Those are populations. And then as we go down the screen, this is the sample distribution if I took samples of size 2. So notice that a uniform distribution becomes almost like an arrowhead. And then as I go to 5, it starts to smooth out a little bit. And as I get to 30, I get a bell-shaped curve. Okay, so uniform population, and as I take bigger and bigger samples, the sampling distributions become more and more normal. Notice for this bimodal one and the second one, population 2, samples of size 2 gets me a peak in the middle, but I still get these little peaks on the side. Okay, so those haven't gone away yet. And then once I get to 5, those have gone away and it starts to look bell-shaped. And once I get to 30, that's a normal distribution. Okay. And then if you look at the skewed right one, samples of size 2, I still have skew, but it's not quite as bad. You can see the other side of this mountain is coming down now. And when I do samples of size 5, you can see I've lost a lot of that skew. I have a peak. I'm still stretching out a little bit this way, but once I get to 30, that distribution is approximately normal. So the idea here is that no matter what population we start with, if I start sampling from it and I start taking bigger and bigger samples, my sampling distributions will become more and more normal the larger my sample size is. Okay, and 30 is kind of the minimum point where we can start saying that my sampling distribution will be approximately normal enough to use z-scores. And obviously, if we continue on from 30 and take samples of size 50 or 100 or 200, that just makes it even more normal. Okay, so z-scores will be even more accurate. So let's do an example here. It says a hot dog manufacturer claims its most popular brand of weenies has an average fat content of 18 grams per hot dog. Suppose the standard deviation of fat content of all hot dogs is 1 gram. Okay, an independent testing organization selects a random sample of 36 hot dogs and finds the average fat content is 18.4 grams. My question is, what's the probability of getting a result of 18.4 grams or more in a sample size of 36? So, what conditions must be met in order to use the central limit theorem to answer this question? Well, to use the central limit theorem, I would like to be able to say that I took a random sample. So they did. It says they took an SRS of 36 hot dogs. I think we can safely assume that 36 is less than 10% of all hot dogs. Okay, companies make millions of hot dogs. And number 3, this is the crucial part, my sample size is bigger than or equal to 30. Since the n equals 36. Okay, so because I have that at least 30 sample size, I can use the central limit theorem. So that tells me that my sampling distribution will be a bell-shaped curve. Okay, and remember the mean of the sampling distribution will equal the population mean. So that was 18. And my standard deviation is going to be the population standard deviation divided by the square root of my sample size. And we had 1 gram as my standard deviation of the population, and my sample size is 36, so I do the square root of 36. So that's 1/6, and 1/6 as a decimal is about 0.17. Okay. Now, the question was, what's the probability of getting a sample mean of 18.4? So here's 18.4, and I want to know what's the chance of getting a sample mean of that large or larger. So I do a z-score, so 18.4 minus 18 over 0.17. So my z-score ends up to be 2.35, which is a pretty large z-score. Remember, a 3 would be almost all the data, so 2 is very large. If I want to find the probability of that, remember we do normal CDF, 2.35 to 10, and I get 0.009. So about a roughly 1% chance of getting this sample. Okay. So not very likely that I would get a sample of 36 to average 18.4 grams of fat. So my last question is, does this result put the hot dog company's claim in doubt? And I would say yes, I think it does. And what I think is the actual fat count, or the actual fat grams per hot dog, is probably greater than 18 grams. Okay, I think they're understating the fat per hot dog, okay? Because the chance of getting a sample of 36 hot dogs to average 18.4 grams is less than 1%. Usually, if the chance of something happening is less than 5%, we think something is up, like that the chance of getting that sample mean is so low that it probably wasn't just by accident, that there probably is something real going on here. So I would say that because the chance of this happening is so small, that they're probably underestimating the fat in their hot dogs. There's probably more fat than they're claiming. Why would you claim less fat? Because a lot of people worry about that. And so when you're purchasing hot dogs, you try to find a hot dog that has the least amount of fat, potentially. So I think they're understating what the fat grams are. Okay, so this is one use of statistics and sampling distributions, is that we can test claims about populations. All right, another example. It says the average number of years that particular washing machine lasts is 7.45 years with a standard deviation of 2.71 years. So my first question is, what is the probability of a washing machine lasting longer than 8 years? Well, I would love to use a z-score to answer this question, but nowhere in the question does it say that this population is approximately normal. So we do not have enough information to answer this question. Okay? You can't just assume that a population is approximately normal. So we don't know if the population is approximately normal. Now, a lot of times, though, and this is important to listen to, just because they say it has a mean and a standard deviation doesn't mean that the population is necessarily normal. Every distribution has a mean and standard deviation, even one that's strongly skewed right. That has a mean and a standard deviation. It's just not a bell-shaped curve, okay? So just because they say it has a mean and standard deviation, every set of data has a mean and standard deviation. We have to know whether or not it's approximately normal to use a z-score, okay? So don't be fooled by that. You have to read the questions very, very carefully. But look at this next question. What is the probability that an SRS of 100 washing machines will average a lifetime of 8 years or more? So now I'm taking a sample of 100 washing machines. Well, if my conditions are met, I can use the central limit theorem, and we can talk about the sampling distribution of 100 washing machines. Okay, so the first thing I would do is check conditions. And number one is random sample, and it did say that they took an SRS of 100. Two, we'll have to assume that 100 machines is less than 10% of all machines, which I think we can assume that. Companies make thousands of washing machines, maybe millions. And then three, and this is the cruel one, we don't know if the population is approximately normal, but n is 100, which is greater than or equal to 30. Therefore, we know that x bar is approximately normal. Okay, so having a large enough sample size kicks in the central limit theorem. So now I know that the mean of my sampling distribution will be the population mean, and the standard deviation of my sampling distribution will be the population standard deviation over the square root of n, and I know that my sampling distribution will be approximately normal. So they tell me the average lifespan is 7.45 years in the population, so my sampling distribution should have that same average. The standard deviation was 2.71 years, but I know I need to adjust that because I took a sample size of 100. So if you divide that, I get 0.271 as my new standard deviation. So notice the standard deviation of this sampling distribution is very small because I took a very large sample. Okay, 100 is a large sample. Okay. So now I want to know what's the chance of these 100 washing machines lasting longer than 8 years. So this would be a z-score. So I do z equals 8 minus 7.45 over 0.271. So I end up with a z-score of 2.03, rounding to the hundredths place. And then we use normal CDF and do 2.03, 10, and I end up with about a 2% chance. Okay, so that tells me there's a 2% chance of finding a sample of 100 washing machines that would average 8 years or more. Okay, so this is a situation where I did not know if the population was normal or not, but because I took a big enough sample, I can use the central limit theorem, and by following those conditions, I can show that the sampling distribution should be approximately normal, which allows me to use z-scores to answer the question. Good luck with using the central limit theorem.